For the last 30 years, the tech industry has shared the same tired joke about quantum computing. It is 10 years away, and it always will be. It was treated as an academic thought experiment. That timeline collapsed in 2025. Governments, venture capitalists, and corporate research labs poured an estimated $33.28 billion into the sector in a single year. Smaller hardware startups are quickly being swallowed up in a massive consolidation wave. Companies like IonQ have spent over $1 billion acquiring firms across the supply chain, turning laboratory theories into commercial, full-stack production lines. The catalyst driving this acceleration is a specific deadline known as Q-Day. This is the moment when a quantum machine becomes stable enough to crack the cryptographic algorithms protecting the world's digital infrastructure. The days of treating quantum mechanics as an academic curiosity are over. We are now in a multi-billion-dollar sprint to secure global data. To reach that finish line, the industry's heaviest hitters are relying on published, highly engineered roadmaps. Google and IBM are currently leading the charge using superconducting qubits. This diagram illustrates Google's recent Willow chip benchmark. It shows how the hardware compressed a calculation that would take a classical computer 10 to the 25th power years to solve into a mere 5-minute operation. IBM is attempting to scale this exact brute force methodology to industrial proportions. Their roadmap targets a massive, fully functioning 100,000 qubit system by 2033. While this approach proves raw computational scale is possible, superconducting systems are highly prone to noise. Keeping that many physical qubits stable requires massive error correction overhead, which could delay their arrival at the Q-Day threshold. Other firms are betting that quality beats quantity. IonQ utilizes a trapped ion approach, working with significantly fewer physical qubits, but ensuring each one is far cleaner and more stable. This timeline plots IonQ hitting the RSA encryption-breaking 1600 qubit mark by 2028. Microsoft's topological Majorana 1 chip provides a third route. Despite relying on entirely different physics, all of these corporate pathways converge in the exact same window. Whether they use superconducting transmon chips or lasers trapping individual ions, the entire global tech industry is uniformly targeting the end of this decade for fault-tolerant operations. Corporate roadmaps are only half the picture. At the geopolitical level, the United States and China have emerged as a strict quantum duopoly, commanding over 60% of the world's total investment. Outside of the security implications, the commercial market is projected to reach nearly $200 billion over the next 15 years. This breakdown chart illustrates exactly where that value is concentrated. The vast majority of revenue is expected to flow from solving complex AI bottlenecks, discovering pharmaceutical drugs, and running advanced climate and material simulations. Dominating the quantum race allows a nation to control the foundational computing infrastructure used across every major industry. This future capability creates an immediate threat, known in the security sector as harvest now, decrypt later. State-sponsored adversaries are actively siphoning massive troves of sensitive encrypted data right now. They can't read it yet, but they are holding it in storage until a Q-Day machine comes online to crack it open. To defend against this, businesses and government agencies are being forced to immediately transition their networks to post-quantum cryptography, or PQC, standards. Since data is being stolen retroactively, any delay in upgrading makes your current archives vulnerable. The era of quantum impact has arrived.